Okay, to start with, I'm going to introduce the terms hydrophobic and hydrophilic, and I'm putting in something called magic sand. So, sand is more dense than water, so it sinks because it's made of silicon and metal oxides, which are very heavy, have a higher molecular weight than water. And what actually happens is when you coat the sand, you coat it with some hydrophobic material, so usually non-polar carbon chains. And so there's only London dispersion forces between them. And so you get this funny effect. You can see at the top there is floating sand, and at the bottom there is this sort of shaped sand, like a bit like a globular curled up protein. So what's actually happening is the water has really strong intermolecular forces, hydrogen bonding, as well as London dispersion, and it's excluding. So you can see it's so strong it's even able to make the sand float, but underneath it's actually excluding the protein. So the protein is, it's actually sand, but it's how protein sort of folds. With the hydrophilic and hydrophobic parts to it, it's actually the water's so interested in itself that it's bonding to itself that it's sort of excluding the weak London dispersion force attracted particles, and that's why it does that. Now going on to the next one. This one's all about looking at, first of all, the density of the two liquids, so which one will sink and which one will float, and then it's looking at, they like to say like dissolves like, which is sort of like a way to sort of memorize it or something, but it doesn't actually give you an understanding of how it works. So you need to always see past the English, because in a test or in a textbook, they're going to ask you to use like dissolves like as a reason for why it does what it does, but that's not really going to give you a full understanding of how things work. You really have to look at the positive attracted to negative and the strength of the positive forces. So first we put water in there, and then water has a lower density than dichloromethane, ethane. So water's 18 grams per mole. Dichloromethane is a much heavier atom, and so that one sinks to the bottom. If you look at the polarity of the bonds, it's only barely polar, so it's really sort of non-polar, and so the top layer is polar. And so what we're saying there, if you look at the numbers, because really if you want to get past, you need to get past the English and look at the forces, and then look at the forces are numbers. So it's really about the math. So water is binding to itself very strongly, and then it's lighter, so it floats on top. Now, if we put something like copper sulfate in, they are ions, so they are very positive and neg, and so that's going to be able to bind better to the very polar bonds of water, and so it's going to be bind to the top layer better than something that has weaker bonds. So the weaker bonds, the dichloromethane, are not going to bind as well, and so they're going to be it's not going to go into that layer, it's going to go into the water layer, because the water layer can hold on to it better because it has a stronger bond, which is the hydrogen bonds, rather than the dichloromethane, which only has London dispersion forces, which are much, much weaker. As you can see, the copper sulfate's not going to go in bind to the non-polar, only borderline polar dichloromethane, the London dispersion forces. It's going to quite happily stay with the water at the top. So now we're just going to add iodine, because that's non-polar. Iodine has only London dispersion forces, so very weak forces. And so the water is not going to prefer to bind to that, because it's very strongly pos-neg. And so that's going to get excluded. So the iodine is going to get pushed out as if it was dichloromethane, and it's going to stay in that layer instead. And so the very weak London dispersion forces between dichloromethane and iodine, it'll get treated as the same thing. And so to say like dissolves like, I think is a little bit inaccurate to say that the dichloromethane likes the iodine. I would say more that the water's not going to grab onto it. Okay? So this one's just a sort of a quick repeat. So instead of using copper sulfate, we're going to use potassium permanganate with water and dichloromethane. And so just like copper sulfate is anions and cations, which are going to be attracted to the most positive and negative thing out there, the potassium permanganate, the same. It's going to be attracted to the most positive neg thing out there, which is not going to be the dichloromethane, it's going to be the water. So you're going to see the pink go into the top layer, which is the water layer. Now, just to reverse it this time, we're going to put hexane, which is less dense than water. So this time water is going to be at the bottom. And so water is going to have a density of 1.0, and hexane, which is going to be completely non-polar, just London dispersion, will be at the top because it's less dense, and water will have the stronger forces because it'll have London dispersion plus hydrogen bonding. And so this time, when you put the copper sulfate in, you'll see that this copper sulfate goes in the water layer, which is the bottom one this time, and the bottom one is blue. So this time we are going to change the non-polar solvent. So we've got water at the bottom and it's mixed with copper sulfate. So those two bind strongly together. And at the top we're going to add hexanol. So that'll be 6 carbons with an OH at the end. First adding methyl red. So we add the methyl red and that'll mix in with the water because that's the only solvent there is. And that actually has a few polar groups in there, but large hexane non-polar groups. And so then when we add a second solvent in there, which is pentanol, I think I might have written hexanol there as the chemical formula, but it's close enough. You'll see that because it's less dense, it will float. And because it is mainly a non-polar group with that little hydroxyl at the end, it's very similar to methyl red, and they'll get excluded. And so those two will go together at the top. And so you'll have the long chain non-polar solvent mixing with the methyl red, and the water and the copper sulfate will be at the bottom. Now, it's not that clear. I add a little bit more copper sulfate in there because I think there was too small amount, or I had to wait. I was being a little bit impatient. It's starting to get a little bit more bluer at the bottom. And so I'll just add a little bit more copper sulfate in there and then give it another mix, and that'll help the layers separate. And so we've separated out the methyl red from the water using that non-polar solvent, which I think I put pentanol in there, but I've written hexanol. But they're very similar with long non-polar chains. Okay, so now this is called salting out. So there's salting in and salting out, and this is just adding a little bit more complexity to it. And to be honest, even with basic solubility, like dissolves like, isn't really going to cut it. It's always positives attracted to negative. And so what you have here is ethanol and water, which actually mix quite well together. In that the water does fit in between the gaps of the ethanol. So if you've got like 50 mils of ethanol, 50 mils of water, it'll make less than 100 mils of total volume. And this time I'm adding the salt, this is potassium carbonate salt, to it. And so the water is now going to have a choice, and it can bind to the salt much, much better. And so it's now going to exclude the ethanol and form a layer. The ethanol is going to be less dense because the amount of carbons per volume will be greater than the water, which will have a lot more oxygens, which are heavier, and so that'll sink to the bottom. Now, I don't know if that's too clear to see the layer here, and so at some point I will add food colouring. So I'm just adding a little bit more. And you can see the amount of water that I added at the start. The layer's not completely separated out. So obviously the ethanol does have some water and salt in there. And the bottom layer will be probably a saturated solution of salt within the water, forming that bottom layer. And there's a lot of leftover water in the top layer still. And I'd have to do further experiments, separate them out, test them to see what's really going on there. But there you could start to see the clear layer at the bottom. and at the top there is the ethanol. And you could test those two layers out and see what's really going on and do further experimentation. But simply a like dissolves like is not going to help you with the complexity of the chemistry, where there's a whole range of positives and negatives doing all sorts of funny things.